Welcome to channel, don't forget to subscribe. Imagine a room filled with the warm, brassy sounds of a big band orchestra. It is July 17, 1981 at the Hyatt Regency in Kansas City, Missouri. More than 1,600 people have gathered in the hotel's soaring, sun-drenched atrium for a tea dance, a nostalgic celebration of music and movement. The atmosphere is electric, a vibrant tapestry of colorful dresses and sharp suits. Couples are swirling on the ground floor, while hundreds more lean against the railings of the majestic suspended walkways that crisscross the lobby high overhead. Then, at exactly 7:05 p.m., the music is punctuated by a sound like a high-powered rifle shot. It is the sound of steel screaming under impossible pressure. Within seconds, a massive shadow falls over the dance floor. Two concrete and steel walkways, weighing tens of thousands of pounds, detach from their moorings and plummet through the air, pancaking on top of one another before crushing the crowd below. Dust fills the air, thick and gray like a fog, turning a scene of celebration into a graveyard of twisted metal and shattered glass. This was not a natural disaster, it was not an act of God. It was the deadliest structural failure in United States history until the collapse of the World Trade Center towers 20 years later. But the most chilling part of this story isn't just the finality of the collapse, it is the revelation we will uncover later in this video, a revelation that proves this entire tragedy was caused by a simple, minor change to a drawing that a professional engineer failed to double-check. A mistake so basic that a first-year physics student could have spotted it, yet it remained hidden in plain sight for over a year. The Hyatt Regency Kansas City was more than just a hotel, it was a symbol of urban renewal and architectural ambition. Completed in 1980 at a cost of $50 million, roughly $180 million in today's money, it was the crown jewel of the city skyline. The hotel consisted of a massive 40-story guest tower and a sprawling 4-story lobby known as the atrium. This atrium was designed to be an urban square, a public space that blurred the lines between the interior and exterior. The centerpiece of this architectural marvel was a series of 3 suspended walkways that spanned the vast open space. These weren't just functional corridors, they were engineering statements. They allowed guests to walk through the air, looking down at the activity below like spectators in a grand theater. To give you an idea of the scale, the atrium was so large it could comfortably house 3 Boeing 747 aircraft parked wingtip to wingtip. The ceiling reached 40 feet into the air, supported by a sophisticated network of steel trusses and expansive glass panels that flooded the space with natural light. The walkways themselves were ribbons of concrete and steel, each stretching 120 feet across the void, nearly half the length of a professional football field. Let's look at the numbers because they are staggering. The 4th-floor walkway alone, constructed from heavy steel beams and thick concrete slabs, weighed approximately 64,000 pounds. To put that into perspective, that is the equivalent of 5 fully grown African bush elephants, or a fleet of 20 mid-sized sedans suspended by nothing but thin steel rods. These walkways were designed to be masterpieces of load distribution, a term engineers use to describe how weight is moved from a structure into the ground. They were suspended from the ceiling by 6 massive steel hanger rods, each 1¼ inches in diameter. On paper, these rods were the lifelines of the structure, designed to carry the dead load of the walkway itself and the live load of hundreds of people. The safety factor, the margin of error built into the design to prevent failure, was supposed to be high. The city's building codes required these walkways to support 100 pounds per square foot. It was designed to be robust, resilient, and, above all, safe. The tragedy of the Hyatt Regency is amplified by the fact that it shattered every assumption we have about modern construction. We often assume that if a building is massive, it is strong. We assume that if a project is handled by prestigious architectural firms and world-class engineering consultants, it is infallible. We assume that because the city issued a certificate of occupancy, every bolt and weld was inspected and verified. The Hyatt Regency was all of those things. It was a state-of-the-art facility, it had undergone rigorous design reviews, it was built by experienced contractors. And yet it failed spectacularly during a routine event. It wasn't hit by an earthquake or a hurricane. It didn't suffer from a gas explosion or an arsonist's fire. It simply fell down under the weight of its own existence and the people it was meant to serve. The collapse was so sudden and so violent that there was no point of no return. The moment the first steel connection gave way, the entire system became a death trap. As we move forward, we have to look past the beautiful glass and the polished granite to see the invisible forces at play. We have to understand how the yield strength of steel, the point at which a material stops stretching and starts breaking, was tested to its absolute limit that night. We have to look at the shear force applied to the bolts and the way the concrete acted as a giant hammer. But more importantly, we have to look at the human element, the decisions made in quiet offices months before the first dancer stepped onto the floor. Because while the physics of the collapse are clear, the chain of human error is what truly haunts the history of engineering. Before we get into the mechanics of the catastrophe, remember this. The Hyatt Regency was considered a triumph of modern design, right up until the millisecond the ceiling began to tear apart. Stay with us, because what the investigators found in the wreckage changed the world of engineering forever, and it all started with a single phone call that went ignored. To understand why those walkways fell, we have to look away from the dust of the lobby and into the quiet, high-pressure offices of the structural engineers and steel fabricators who designed it. The project's engineering was handled by Jack D. Gillam and Associates, a firm that was, at the time, a leader in the industry. But in the late 1970s, the fast-track construction method was becoming popular, a system where construction begins before the final designs are even completed. This environment of haste created the perfect breeding ground for a minor clerical oversight that would eventually kill 114 people. The original blueprints for the Hyatt Regency featured a design that was elegant and fundamentally sound. It called for 6 continuous 1¼ inch thick steel hanger rods to run from the heavy ceiling trusses all the way down to the second-floor walkway. In this single-rod design, the 4th-floor walkway and the 2nd-floor walkway would both hang from the same set of rods independently. Imagine a single long rope hanging from a tree branch with 2 people holding onto it at different heights. The person at the top only has to hold their own weight, and the person at the bottom only has to hold their own weight. The rope itself carries the total load, but the individual grips of the people are independent. This design had a massive load capacity and met all Kansas City building codes with a comfortable safety margin. However, when the plans reached the manufacturer, Haven Steel Company, they flagged a major logistical problem. They didn't have the capability to thread a 45-foot-long steel rod across its entire length without damaging the threads or using incredibly expensive specialized machinery. To simplify the assembly, Havens proposed a change. Instead of 1 long rod, they would use 2 shorter offset rods. 1 rod would connect the ceiling to the 4th-floor walkway, and a second separate rod would hang from the 4th-floor walkway down to the 2nd floor. On a busy morning in early 1979, a technician at the engineering firm received a phone call about this change. Without performing a single new calculation or sketching the physics of the new arrangement, the firm gave the green light. They treated a fundamental structural shift as a mere shop drawing revision. This was the fatal turning point. By switching to a 2-rod system, the engineers inadvertently doubled the stress on the 4th-floor beam connections. In the new configuration, the 4th-floor walkway was no longer just hanging from the ceiling, it was now acting as the anchor for the walkway below it. To return to our analogy, instead of 2 people holding a rope separately, the person on the bottom is now hanging onto the ankles of the person above them. Now the person at the top has to support not only their own weight, but the entire weight of the person dangling below. This stacking of the load meant that the box girders on the 4th floor were being crushed by twice the weight they were ever designed to handle. Let's talk about the physics of yield strength. Every material has a limit, a point where it stops being elastic and starts to permanently deform. The box girders were made by welding 2 steel C-channels together. The hanger rods passed through these girders and were secured by a nut and a washer. In the original design, the nut only had to hold the weight of 1 floor. In the revised design, the shear force, the force trying to slide the rod through the beam, was doubled. The steel was literally being pushed to its yield strength before a single person even stepped onto the hotel's property. The load capacity of the connection, which should have been at least 30,000 pounds to be safe, had been accidentally slashed to less than 8,000 pounds. Even more terrifying is that the design didn't just fail to meet the extra safety requirements, it failed to meet the basic requirements of the weight of the concrete itself. The dead load, the weight of the walkways when empty, was already stressing the steel to nearly 100% of its capacity. There was no room for live load, which includes the people, the wind load from the atrium's ventilation system, or the rhythmic vibrations of a dancing crowd. Engineers often use a safety factor of 2.0 or 3.0, meaning the structure is 200% to 300% stronger than it needs to be. The Hyatt walkways after the design change had a safety factor of approximately 0.6. In the world of engineering, a safety factor below 1.0 means the structure is already in a state of active failure. The metal fatigue wasn't the primary killer here, it was a total structural bypass. During the investigation, it was discovered that the box girders were so weak that the nuts were literally pulling through the steel plating. As the dancers moved to the music on that July night, they were unknowingly creating a dynamic load. Every step, every synchronized movement of the crowd sent waves of energy through the steel. The angle of inclination of the rods began to shift as the beams warped under the impossible pressure. We are talking about tens of thousands of pounds of concrete and steel hanging by a literal thread of misinterpreted mathematics. There was one final warning sign that the world ignored. In October 1979, during the hotel's construction, a 2,700 square foot section of the atrium's glass roof collapsed. The engineers blamed a faulty connection in the roof trusses and performed a quick inspection of the rest of the building, but they were looking for errors in the roof, not the walkways. They were so confident in their computerized models and their professional status that they never bothered to walk over to the walkways and check the most critical connections in the building. They had multiple chances to see the bowing of the steel beams, but they were blinded by their own assumptions. The point of no return had been crossed months before the first guest checked in. The clock was ticking, and all it took was the sound of a big band orchestra to bring the whole house down. At exactly 7:05 p.m., the music of the Steve Miller Orchestra was playing a upbeat rendition of Satin Doll. The lobby was a kaleidoscope of movement, with over 1,600 people filling the floor and the overhead bridges. Then the atmosphere shattered. Witness accounts describe a sound like a high-velocity rifle shot, the crack of steel failing under tension. On the fourth floor walkway, the connection at the middle set of hanger rods simply gave way. Because the structure was now interconnected in a deadly chain, the failure of one connection triggered an instantaneous progressive collapse. The fourth floor walkway, weighing 64,000 pounds, roughly the weight of a fully loaded semi-truck, plunged vertically. It fell 15 feet onto the second floor walkway directly beneath it. The second floor structure, already strained to its breaking point, stood no chance. It was instantly crushed, and the combined mass of nearly 130,000 pounds of concrete, steel, and human beings slammed into the crowded dance floor below. The entire collapse took less than 5 seconds. In the time it takes to draw a single breath, a palace of modern luxury became a scene of industrial carnage. The sound was deafening, a roar of grinding metal followed by a thud that vibrated through the very bedrock of Kansas City. Then there was silence, quickly replaced by the sound of high-pressure water lines bursting. Gallons of water began to flood the lobby, rising around those trapped under the debris. Dust from the pulverized concrete hung in the air like a thick, gray curtain, making it impossible for survivors to see more than a few inches in front of their faces. This wasn't just a building failure, it was a physical pancake effect, where the weight of the upper floors added kinetic energy to the destruction of the lower ones. The human cost was staggering. 114 people were killed and 216 were injured. Many of the victims were prominent members of the community, doctors, teachers, and business owners. One of the most haunting stories is that of Dr. Joseph Weckerle, the director of the local emergency department, who was actually attending the dance. He found himself performing battlefield triage in a tuxedo, crawling through the twisted wreckage to reach those pinned beneath the slabs. Rescue workers had to use jackhammers and even a crane to lift the massive concrete segments. To understand the weight they were dealing with, one single slab of the walkway was as heavy as 4 school buses. It took nearly 14 hours to extract the last survivor from the ruins. The investigation that followed was one of the most exhaustive in the history of the National Bureau of Standards, (NBS). Lead investigator Edward Frank and his team treated the atrium like a giant crime scene. They quickly focused on the box girders, the steel beams that the hanger rods passed through. When they examined the wreckage, they found a chilling piece of evidence. The steel plates where the rods were secured had been deformed into a tulip shape. The nuts and washers had literally been pulled through the solid steel of the beams. This confirmed their darkest suspicion. The connection didn't fail because of a manufacturing defect in the steel. It failed because the design change from a single rod to a double rod system had doubled the load on the connection, pushing it past its ultimate tensile strength. The NBS report was a stinging indictment of the engineering process. It revealed that the walkway design as built could only support 53% of the load required by the Kansas City Building Code. This means the structure was failing from the moment it was finished. It was so weak that the weight of the people dancing was simply the final straw for a system that was already in a state of terminal stress. The investigation didn't just look at the physics, it looked at the communication protocols. They discovered that the engineering firm Jack D. Gillam and Associates had signed off on the fabricator's revised shop drawings without ever performing the math to see if the new two-rod system was safe. The legal and professional fallout was unprecedented. In 1985, the Missouri Board of Architects, Professional Engineers and Land Surveyors found Jack Gillam and his lead engineer, Daniel Duncan, guilty of gross negligence, misconduct and unprofessional conduct. Both men had their professional engineering licenses revoked in the state of Missouri and several other states. It was a landmark case because the engineers were held responsible for the shop drawing errors of the fabricator. The court ruled that the engineer of record bears the ultimate responsibility for every structural element of a building, regardless of who draws the plans or suggests the changes. Over $140 million, nearly $500 million in today's currency, was paid out in civil settlements to the victims and their families. The Hyatt Regency collapse became a permanent scar on the history of Kansas City and a cautionary tale that is taught to every engineering student in the world today. The dust settled on the Hyatt Regency lobby, but the shockwaves from the collapse were just beginning to reshape the entire landscape of global engineering. This wasn't just a failure of steel, it was a failure of the professional social contract. Before 1981, the process of reviewing shop drawings, the detailed diagrams created by manufacturers and fabricators, was often treated as a bureaucratic formality. Engineers would frequently stamp these documents with "approved" without performing rigorous verification, assuming the fabricator had done their own due diligence. The Hyatt tragedy ended that era of complacency forever. It forced the American Society of Civil Engineers, ASCE, to adopt a radical new policy. The Engineer of Record, EOR, now bears the absolute non-transferable responsibility for the structural integrity of every single component in a building. If a bolt fails, if a weld snaps, or if a minor change is made to a hanger rod, the legal and ethical liability rests solely on the shoulders of the licensed professional who signed the master plans. This change in legal accountability is the reason why, when you walk through a modern airport or a soaring skyscraper today, you are safer than guests were in 1981. The reforms didn't stop at legal liability. The Hyatt collapse led to the creation of mandatory peer reviews for complex structures. Today, if an architect proposes a daring new design, a second, independent engineering firm is often brought in specifically to find the flaws that the original team might have missed. This red teaming of engineering prevents the tunnel vision that led Jack Gillam's firm to ignore the warnings in the atrium. Furthermore, building codes across the United States and the world were rewritten to specifically address the progressive collapse phenomenon. Engineers must now design structures so that if one connection fails, the rest of the building can redistribute that load, preventing the pancake effect that proved so deadly in Kansas City. This is often referred to as structural redundancy, the engineering equivalent of having a backup parachute. Is the difference between a minor repair and a total catastrophe. To visualize this, think of a bridge held up by many cables versus one held by a single rod. In a redundant system, the failure of one link does not cause the entire chain to snap. To understand the weight of this legacy, we have to look back at the history of human ambition. The Hyatt Regency was not the first time we learned this lesson the hard way. In 1907, the Quebec Bridge collapsed during construction because the engineers underestimated the dead load of the steel, killing 75 workers. In 1940, the Tacoma Narrows Bridge twisted itself apart in the wind because designers didn't account for aerodynamic resonance. Each time the lesson was the same: when we push the boundaries of scale and beauty, the margin for error shrinks to zero. The Hyatt tragedy is a mirror of systemic decisions. It shows us that a disaster is rarely the result of a single bad apple. Instead, it is a chain of small, seemingly insignificant choices: a rushed phone call, an unverified drawing, a missed inspection, a desire to save time, that eventually align into a perfect storm of failure. It is a reminder that in the world of megaprojects there is no such thing as a minor detail. Every nut, every bolt, and every decimal point is a potential point of failure. The Hyatt Regency Hotel still stands today, now operating under a different brand name, and the lobby has been completely renovated. The suspended walkways are long gone, replaced by a massive ground-supported second-floor balcony that is physically impossible to collapse in the same way. Just a few blocks away, a memorial stands with the 114 names of the victims etched into stone, a permanent, somber reminder of the true cost of a mathematical error. This story isn't just about physics or yield strength. It's about the ethics of responsibility. It's about the silent trust we place in the people who build our world every time we step into a public space. Every time you cross a high-suspension bridge or walk through a glass-domed mall, you are trusting a stranger's math and their professional integrity. The Hyatt Regency taught the world that this trust must be earned through constant vigilance and unyielding professional standards. Thank you for joining us on this deep dive into one of the most significant engineering failures in history. If you found this breakdown of the mechanics and the aftermath of the Kansas City tragedy insightful, please hit the like button and don't forget to subscribe for more stories of human ambition, engineering disasters, and the lessons we learn from our greatest mistakes. We want to hear from you in the comments. In our modern world of high-speed construction, AI-assisted design and massive budgets, do you think we are doing enough to prevent another Hyatt Regency, or are we destined to repeat these mistakes as we build even bigger and more complex structures? Who do you think was more responsible? The engineer who signed the change or the fabricator who suggested it? Let's get a discussion going below. Until next time, stay curious and stay safe.